Our meeting, our symposium, our work, and next keynote speaker, very well-known Paolo. Paolo is really bright and smart and nice and excellent and perfect and so on. Scholar and scientist. A little bit lost in his life, but never mind. Please start, it's your time now.
Thank you to Vincentas for his kind invitation and for his, do you hear well? Okay, and for his introduction. Briefly, I introduce myself. My name is Paolo Bussotti and I teach history of science and history of mathematics at the University of Udine. So, Udine is this place in northwest Italy where I work. It is indicated by the point of the arrow. The place where I live half of the year in instead my native place, which is Livorno, which is in the west of Italy. It is indicated by the point of the arrow. So, this presentation is closed. Udine and Livorno, my two cities, so to say. Now, we will speak of the introduction of the notion of energy. First of all, as I have told, I am not exactly an expert in science education. I am a historian of science, and I hope that some contributions coming from history of science might be useful for science education. Of course, you who are the experts in this field have to judge if this is the case. I have chosen the case of energy because it has many interesting questions behind. First of all, it was a notion which nowadays is spread in the whole of physics, but its birth is relatively recent because it was born in the middle of the 19th century. Therefore, it's a relatively recent concept in comparison, for example, to that of force. The second question is that connected to the concept of energy, there are those of heat and of work. And heat and work are two fundamental notions of our daily life, as energy is. And the notion of energy was born exactly because of necessity deriving from our daily life. And after that it became one of the most general and abstract concepts in the whole of physics. Of course, I am not claiming a theory of the way in which, in general, the scientific concepts are born, because there are concepts which are born in a purely theoretical way. For example, Newton's concept of force, or the concept of general and special relativity. They are born in a purely abstract manner, no connection with the daily life. While from the concept of work, heat and energy, this is not the case. There is a strong connection with the daily life and with the problem that society had to face in that period. Okay? So, my idea is that this historical consideration can be introduced in a classroom. Of course, I am thinking of a classroom in the high school, in the last 3 years of the high school. It depends on the different countries, because the concept of energy in Italy is taught at the 4th year of the high school. I don't know in the other countries, but I think in the last 3 years of the high school. So, coming in our context, energy is probably the most important concept in physics because it regards all the fields of physics. It pervades all the branches of this discipline. What is a common definition of energy? A common definition considers energy as the physical quantity which measures the ability of a body to perform a work. Of course, we should define work, we should understand what work is, but at the beginning this appears an acceptable definition of energy. But in fact it is not, or at least it is not a complete definition, because energy has physical manifestation which cannot reduce to work. The most important of these manifestations are, for example, heat and light. And these two concepts are not exactly reducible to that of work. Therefore, one of the most clever physicists ever, which is Richard Feynman, in his lecture on physics, in the first volume of his lecture on physics, proposed this definition of energy. I read what Feynman wrote. There is a fact, or intuition law, governing all natural phenomena that are known to date. There is no exception to this law. It is exact as far as we know. The law is called the conservation of energy. It states that there is a certain quantity, which we call energy, that does not change in the manifold changes which nature undergoes. That is a most abstract idea, because it is a mathematical principle. It says that there is a numerical quantity which does not change when something happens. It's not a description of a mechanism or anything concrete. It's just a strange fact that we can calculate some number, and when we finish watching nature go through her tricks and calculate the number again, it is the same. Of course, this is a very abstract definition of energy. It's true, but it's abstract, and it is too abstract to be presented in a high school context, I think. Pupils will understand nothing about what energy is. On the other hand, this is a correct definition. Therefore, an itinerary should be conceived which makes Feynman's word comprehensible. This is the reason of my talk. And in this itinerary, I think that the historical genesis of the concept of energy is useful. As it's always the case, it's better to adopt a test as a guiding test. And in this case, I have chosen a text written by Helmholtz, a famous German physicist. He wrote this text in 1854, and the English translation you can find freely on the internet. The English translation is on the interaction of the natural forces and the most recent determination of physics connected to it. Forces in this context means energy, not Newtonian force. Okay? So, we are in 1854. Why did Helmholtz write this paper? Because in the preceding decade, he himself, Robert Meyer, Joule and Kolding, who was a Danish physicist, whereas Meyer was German as Helmholtz, and Joule was English, discovered the concept of energy and discovered the principle of energy conservation. Therefore, in a didactical itinerary concerning energy, in my opinion, it's appropriate to introduce energy through this work by Helmholtz. Of course, this is appropriate to give a general idea of what energy is, because it is important that the pupils, that the learners understand that this idea is not restricted to mechanical energy, it's not restricted to potential and to kinetic energy. It has more manifestations. Of course, after this general introduction, it's necessary to offer a mathematization of the concept of energy. And in this case, it's necessary to come to a more traditional approach. And this is the second step. I have written quantitative determination to energy. The two main fields which can be used to understand what energy is are, in my opinion, mechanics and thermodynamics. Of course, there is electricity, there is electromagnetism, this is obvious, but in the context of the high school, it is possible to make everything. As Gauss told, pauca sed matura, few things but well done, better than many things but not well done. So, why is the birth of the concept of energy connected to our daily life? Because Helmholtz tells us, and this is known, that in the 17th and 18th century there was the Industrial Revolution, and of course there was the need to produce work. For the moment, let us this word its intuitive meaning, okay? It was necessary to produce machine which replaced human work. And what was one of the most important attempts of the inventors of that time? To construct a perpetual motion machine. What is a perpetual motion machine? It is a machine which is self-powered. It's not necessary to add new energy to this machine. It can produce work continuously. This was the idea. All the attempts failed till the point that in 1775 the Royal Academy of Science of Paris closed their attempts to the papers which proposed a mechanism which offered a perpetual motion. They denied this possibility, but there was no theoretical reason why this was not possible. Theoretically, it could be possible, but all their attempts failed. So, the first step, the physicists posed the problem, why do these attempts fail? And the first answer to this question was the definition of the concept of work. How did we arrive to this definition? Helmholtz take this example. Consider a water mill. A water mill is a mechanism, in the slide is explained the mechanism, through which it's possible to perform several kinds of tasks. One of these kinds is the possibility to elevate a hammer so that the hammer falls, it hits a piece of metal and it changes its form. Therefore, the task of the mill is to elevate a heavy hammer. Okay? How is this possible? First of all, the machine has to win the weight of the mass of the hammer. I have called this mass m. And of course there is the gravity acceleration. Therefore, it's necessary to win a force mg, which is the weight of the hammer. This means that if the weight is double, the work is also double. On the other hand, the effectiveness of the hammer blow on the metal mass depends not only on the weight, but also on the height from which the hammer falls. If it falls from a higher height, it's more effective than if it falls from a lower height. Well, these concepts were known, but no one gave a formal definition. The first one who gave a formal definition was a French physicist and engineer who was Coriolis, and who is well known for other reasons, because of the apparent force which is today called Coriolis force. But he was also the inventor or the creator of the concept of work. And he defined work by force, by displacement, by the cosinus between the force and the direction of the displacement. Because if a force is perpendicular to the displacement, it produces no work. What today we use the definition through the scalar product, F dot ds, is a later definition, which is obviously equivalent to the one given by Coriolis, because in 1829 the vector calculus does not exist. Therefore, Coriolis did not have the concept of scalar product. The vector calculus in our form is a product of the late 19th century. Hamilton gave some anticipation, so to say, but in our form it dates back to the end of the 19th century. Now, it's appropriate to remark that the three Newtonian principles teach us that to leave the hammer of a mass m at an 8, let's say h, it is at least necessary to use an equivalent mass. I have written of water because I was speaking of a water mean, but of any material which falls from the 8th h. Experience shows us, and it is important because for what we will say, experience shows us that in almost every concrete case, the mass of the water has to be bigger than m, or the h bigger than h. Okay, so far we have defined what work is, and we have analyzed the work necessary to elevate, necessary to hit a hammer to elevate h. But now, let's wonder another question. Why does the hammer modify the metallic mass if the hammer itself moves and is not at rest? The answer is rather obvious. Work is only a function of velocity. It's not only a function of mass, it is also a function of velocity. Why is this important in the context of energy? Why? Because three great physicists of the 17th century, therefore many years before Coriolis, had invented a concept which they call living force. They write in Latin and they call this concept vis viva. The vis viva is the product of the mass by the square of velocity. And they used vis viva to solve simple problems. They tried to give a general theory of the vis viva, but they were not able to do it. They used this concept to solve singular problems, in general connected to the gravitational fields. Now, let us come to a further analysis. And after that there is a slide which closes this first part of our itinerary. If our hammer would fall on a very elastic lamina, suppose not on a block of metal but on elastic lamina, in the best circumstances it would bounce to the same height, not higher. In the best circumstances, to the same height. This means that the living force can produce the same quantity of work as that from which it has been generated. It cannot produce more work, but the same quantity of work. There are numerous examples of communication of the vis viva to produce work. A man winding a watch communicates to the mechanism of the watch a living force. That watch returns over the next 24 years. Why? Because it has to overcome the problem of the friction, of course. What is work, therefore? Work can be seen a way to communicate living force between two physical systems, or between two different states of the same physical system. So, now, let's come to the first conclusion. On the right, you see the relation between work and living force, that now we call kinetic energy. That is, work is the difference, if we analyze two physical states, work is the difference between the kinetic energy of the final state minus the kinetic energy of the initial state. Therefore, in this brief itinerary connected with history, we have understood why work was introduced and how work explained the meaning of the vis viva, so mysterious. As a matter of fact, the old physicists had understood something profound, but they were not able to give a systematic vest to their discovery. In 1829, Coriolis did, and Helmholtz tell us this history. So, it's a particular, but it is important. There is 1 divided by 2, mv square, no mv square simply. And it's obvious, because we have to integrate v, the v, and we obtain 1 meter. 1 divided by 2. It's an elementary integral. Okay? Well, at the end, we can say that machines do not produce any impulsive force, but simply they communicate kinetic energy given to them through work, so that energy is transformed but is not created, and work is a means to transmit energy from two different states of a system. Okay? As I have written, machines do not produce any impulsive force, but simply communicate the kinetic energy given to them through work, which can thus be seen as the energy exchanged between two systems when a displacement takes place. Machines are ergo mechanisms which transforms energy. Okay? But now, things are more interesting and more complicated than this, because now our pupil knows that the elementary work can be defined as force by elementary displays. Now let us consider the action of gravity. We know that the weight of a body is mg. Then our concept of work, of elementary work, can be written as mg dot dh, where h is an infinitesimal difference of 8, of course. Plus a constant, and this is obvious. We have to integrate, and when we integrate, we obtain a constant as well. In the elementary form, there is not the constant, but when we obtain the finite form, there is a constant which has to be added. So, when a body of mass m is at an age h, but is at rest, is produced no work. But there is an interesting fact. it has the potentiality to produce work. Potentially, it can produce work because as soon as the gravitational force acts on the body, work is produced. When the body reaches the soils, a work mgh is carried out. But in this way, we have defined a new function. mgh can be defined as the potential energy of a body in a field. Of course, we are speaking in historical terms to make things easier, therefore we should restrict to gravitational field, okay? Because the concept of potential energy is born in a gravitational context. So, the difference between initial and the final values of potential energy indicate the work performed by the body. On the other hand, we have seen that the work performed by the body is also indicated as the difference between the final kinetic energy and the initial kinetic energy. These two quantities are equal, which is the immediate consequence that the sum of the initial and of the final kinetic energy, considering the sum of potential and kinetic, is the same. Therefore, in this way, we have seen that as Feynman says, there is a quantity which is conserved. And this is mechanical energy, because the sum of kinetic energy plus potential energy is called mechanical energy. One can say, okay, we are ready, everything is in order. Are the things so plain? No, they are not so plain. And to explain this, it's necessary to come back to Helmholtz, which continues to tell this very interesting story. Because until now, we have considered only motive forces. But there are many phenomena which are not directly connected to the motions. Let us think, of course, partially they are connected to motion, but not completely. Let us think of heat, electricity, magnetism, light, chemical forces, and so on. And they have different, obviously they have connection with motive force, but they are not produced directly by motive forces. What happens? That mechanical work can also be produced through not exclusively mechanical processes. Let us think of this easy example. If a container, relative to the diagram, if a container with gas is closed by a moving piston carrying weights, when the gas is heated, it expands because of its increasing kinetic energy and the energy of its particle, and the piston goes up and the weight moves. Therefore, heat, in this case, can produce work. Now, there is the fundamental question, which is also connected to one of the most profound concepts of physics, which is the concept of entropy. And the question is this: what is the connection between heat and work? In this case, we have seen a large connection and not precise connection, because it's not precise, we have seen only an example. Well, the first who posed this question was Robert Meyer in 1842. Robert Meyer, who was one of the discoverers of the principle of conservation of energy. It's very interesting to point out that he was a physician, not a physicist. He knew physics, of course, but basically he was a physician. And he was in Java with the army. With the army. He was an army doctor. He was in Java and he noted two very strange phenomena. The first, the wind-swept waves are hotter than the water of the calm sea. He measured the temperature and he saw that the calm sea is colder than the waves. And the second phenomena is even more interesting. Here I present the phenomena. There are many chemical experts who knows the phenomena better than me, therefore I hope to make no mistake. Lavoisier understood that the animal heat is the result of a combustion process. On this basis, he realized that the change in blood color as it passes from the artery to the veins is a sign of the oxidation of the tissues. In order to maintain the body temperature, the production of heat through food is associated with the loss of heat. This loss of heat depends also on the temperature of the environment. If the temperature is low, more food is burned. This produces a bigger oxidation, which in its turn makes the venous blood darker. Therefore, what should be expected? That the difference in color between the arterious blood and the venous blood is bigger at our latitudes than in Java. And this was exactly what Meyer saw. The difference in the venous and arterial blood in Java was minimal, whereas at our latitude it is evident. Meyer then wondered how could an organism produce heat and what is the relation between the movement and heat. Well, he gave some hypothetical answer, relatively precise but not decisive. The decisive answer concerning the relation between movement and heat arrived from a German physicist who was Joule. What did Joule do? He was able to reach a precise determination to the following brilliant experiments that now I summarize. He considered a water-like container filled with water. Inside this container, he put pedal-shaped wheels rotating on an axle, like in the figure in the higher part of the slides. On the outside, tied to two pulleys, there were two weights, which are indicated and which called fall down. When the weight arrived at the basis, what did Joule do? He made a measuration. He measured the potential energy at the beginning of the two weights. He measured the kinetic energy of the two weights when they reached the soil, and he found that they did not correspond. The potential energy at the beginning was bigger than the kinetic energy at the end. This means that a part of the energy was transformed in heat, because on the other hand, he had put a thermometer inside the vessel and he had discovered that the water had become hotter than at the beginning. Therefore, what did Joule do? What did he understand? Of course, this was the first experiment developed by Joule. The result was so important that he developed a long series of experiments, and this experiment gave all the same result. Therefore, what did Joule think? That, in a sense, the nature of heat is similar to that of the work. In what sense? In a relatively precise one, because both of these magnitudes are a way of transferring energy and transforming it in different forms. Therefore, of course, work is measured in joule, heat is measured in joule, but they're not exactly energy. They are a way of transporting and transforming energy from one body to another, from one system to another. So we have seen mechanisms which allows us to transform heat in work and work in heat. But is this transformation completely possible? In particular, is it completely possible to transform all the heat in work? Is this possible? Well, before I try to answer this question, we can say that we have reached, however, an important conclusion. Which is the conclusion? There is a quantity which is conserved, and this quantity is energy. It has various forms, and we have spoken of potential, kinetic, and thermal energy. Mechanical energy is not conserved in every process. If a process produces heat, a part of energy is lost through heat and became thermal energy. Now the question is, there is the possibility to retransform this thermal energy into kinetic energy so as to obtain a new work? Well, the answer is, it is possible, but only partially and only at well-determined conditions. In general, most part of heat is lost. This does not mean that energy disappears. Of course, it does not disappear. Energy is conserved. But what is not possible to reobtain is the same form of energy. In particular, it's not possible to reobtain a form of energy which not only interesting for us, but the form of energy which allows the change in nature. And what is this kind of energy? Of course, mechanical energy. It is mechanical energy which allows the changement, which allows the movement. This is, so to say, the good part of energy. There is a part of it which cannot be anymore utilized as mechanical energy. It cannot be once again transformed into mechanical energy. So now, okay, let us now, how much time do I have? 5 minutes. Okay. What did Helmholtz, Joule and Mayer understand? That if all bodies in nature, first of all, they understood that the heat passes from a colder body from a hotter body to a colder one. This is, it can seem natural, but it's written nowhere that heat passes from a hotter body to a colder one. It's a principle which was discovered. Now, which is the problem? That this mechanism makes a part of the energy of the universe impossible to be utilized for further changement. Because if a body is put in contact only with hotter body, that body can produce no work. The hotter body can, but that body can't. Because a difference of temperature is necessary to transform heat in work. Now, what is the tendency of the processes? Is that all the body reaches the same temperature. Is this clear? If the heat passes from hotter body to colder bodies, the tendency is that all body of the universe tend to reach the same temperature. Okay? And when all the bodies have the same temperature, is it possible to produce further work? Obviously no. It's not anymore possible. It's not anymore possible. This is the concept of thermal death of the universe. And this was a concept which was reached in 1854 by Helmholtz. Of course, this concept is, as a matter of fact, the concept of entropy. To reach a definition of the concept of entropy, 10 other years were necessary, and was Clausius who defined the concept of entropy, but as a matter of fact, Helmholtz had already reached the concept of entropy. Therefore, in our didactical itinerary, we have started from the notion of work. We have analyzed how work is connected to energy. At the beginning, how work is connected to vis viva. We have seen or potential energy, or kinetic energy. We have seen that it's necessary to introduce a new concept. This concept is that of potential energy. And we have reached a general picture of mechanical energy. After that, thanks to the experiment of Joule, thanks to the intuition of Mayer, and thanks to the experiment of Joule, we have understood that it is not enough to define energy. Mechanical energy is not enough. It is at least necessary to add heat. We have seen the role of work and heat, and we have seen that the relation between energy, work, and heat can also be important in order to introduce such an abstract notion as that of entropy. Therefore, starting from an historical context, in a relatively few lectures, I think 6 or 8 hours can be enough, it's possible to give to the pupils a precise idea, of course qualitative idea, of these such difficult phenomena. In the rest of the slides, I have spoken in some more detail of the entropy, but now we do not have time. But anyway, I have introduced the idea, which my idea is. So I arrive at the conclusions. Well, and which are my conclusions? First of all, before considering the mathematical details concerning the various forms of energy, it's appropriate to introduce this concept following a historical approach, because this approach is particularly suitable for the pupil to gain the real nature of energy. While speaking of energy, it is almost impossible to prescinde from thermodynamics. Of course, during the year, I understand that mechanical energy is taught before than thermodynamics. This is comprehensible, but in my opinion, it's necessary to give 4 or 5 introductory and general lessons in which one explained the origin and the meaning of the concept of energy. And there it's necessary to speak of it, saying, okay, pupils, this concept will be clarified in the future. But now I give you the general picture. This is important, in my opinion, for the pupil to have an idea and to follow a logical way of reasoning. This is important, I think. Finally, I conclude that in this period, the term multidisciplinary and interdisciplinary are widely used, but there are not many concrete examples of how to apply them, and this is a little example, because this could be developed, for example, jointly with the teacher of history. Why the necessity to define work? Because human society was changing, because industrial revolution was present, and it was necessary to have more production, it was necessary to define better some scientific concept. This is the reason why the concept of work was defined by Coriolis, who, not by chance, was basically an engineer. Coriolis was an engineer, he was not a theoretical physicist. He became a theoretical physicist in the second part of his scientific career, but basically he was an engineer. Therefore, this example shows a profound link between the development of society and the development of scientific concepts. Of course, this is an example. I repeat, I am not claiming that this is always the case. In this specific situation, the link is clear. Okay, I conclude here. I think 50 minutes, 48 minutes.
So, thank you very much, Prof.
Really 5 minutes more like was planned, but we have few times for questions, 1 or 2 questions. Sasha, please.
I have questions. Paolo, thank you for your presentation. Me and you, I'm teaching history of science and history of chemistry. So history of chemistry. Yeah, so I really enjoyed. One famous astrophysicist, Brian Cox, said that the beauty of science lies in story. So we need to tell stories about forming knowledge through history to our students. I have a question. Have you ever had opportunity? I suppose that you had opportunity to see textbooks for high schools in Italy, and how much context of history is represented in textbooks in Italy?
Okay. I think it is a challenge for new lecture, but we don't have time for new lecture. Short response.
That's a very good question, and my answer is clear. History of science is almost not considered in an educational context. Almost not considered. And when it is considered in a wrong way. I mean, there is the theory, and after that, 10 lines on the history of science, which are only anecdotes, and which makes the things out of their context, and almost negative in a sense. Better to avoid almost than 10 lines. In my opinion, it's, I don't say necessary, but it is preferable to introduce science through an historical context. Of course, the technical part is necessary. I am absolutely favorable to the technical part. But an historical introduction is necessary. It is appropriate. But it has to be well done. Not 10 lines like a note. Otherwise, it seems that the scientists are these strange people who think who knows. No, they were hard workers. They were concentrated on their field. So, if it is made serious, history of science is fundamental for improving didactics of science. Otherwise, better than
Paolo, maybe 10 lines is better. Example, like only faith.
Yeah.
Okay, thank you for the question. And next one, Solange, please.
Paolo, congratulations for the presentation. Thank you. I'm very curious about your presentation. It was very nice. And as a teacher, and I think everybody here the same way, we are in the same page, because I'm used to teach about entropy. And this concept is so difficult because in high school, they don't never been through this concept. So, what would you suggest to give a class of entropy, a basic concept, not too deep, considering the historical approach? For example, for undergraduate students, how could I do? Because you said it's totally true. Yes. Oh, I'll give you a historical approach. I'll talk about some scientists and okay, I'll give you entropy. No, this is not historical approach. So, what would you suggest? I know it's not easy, but in simple words, what would you help us, please? Thank you.
Okay, I try to answer briefly because the answer should be very long.
Also topics for new lecture.
Yeah, as briefly as possible. Of course, there are two possibilities to introduce to history entropy. Either to Clausius approach or to Boltzmann approach. Boltzmann approach is in a sense easier, thought more profound, because it is based on an easy statistical fact. Look at these lines. In how many configurations you have 6 parts of a gas? In how many configurations it's possible that 6 parts are of the left side and the right side is completely empty? 1 configuration. How many configurations are possible? 5, 1. 6 configurations. How many configurations? 4, 2. 15 configurations. How many configurations? 3 and 3. 20 configurations. This means that for us, disordered configuration is the most probable. And of course, when the quantity of gas is 6 molecules, the difference is not so huge. But consider that in a room, on average, there are 10 elevated to the 26 molecules. Therefore, when the number is so high, the possibility to have the division n, that is all full, is by far superior, by far. This means that the equilibrated configuration, when no more work is possible, is by far the most probable, by far. And this indicates another profound fact, that the time has an arrow, because it's not impossible that the gas is distributed like in the first image, but it's so unlikely. The probability is so low that, as a matter of fact, you see the time which goes in one direction, that is in the direction of the uniform distribution, not in the opposite direction. It's not impossible. Theoretically it's possible, but the number of combinations is so low that, as a matter of fact, it does not happen. And this justifies the error of time.
So I was worried. I was worried that it is inspiration for new questions. But we have to break this discussion. Oh, sorry for it. Thank you very much for very nice, interesting, but heavy presentation. I studied also physics, but I know what is it. But thank you very much.
I understand. These vibrations are more, there are more vibrations in the same time. Because it's smaller. I understand. They are heavier and vibrate less. Okay.
The same philosophy like orgle. They're blowing.
This is extremely. No, this is maybe for this. No, I live here.
Yeah.